Hello everyone, this is a brief introduction to our paper investigating the reordering capability in CTC-based non-autoregressive end-to-end speech translation. I'm Myung-Song Chuang. This work is a joint work with Shun-Po, Chih-Chiang, Chang, and Hongyi Li from National Taiwan University. In speech translation task, we have a source audio, and we want to translate it into text in another language. The autoregressive decoding process in this model is very time-consuming. As a result, we want to build a non-autoregressive speech translation model using transformer to output the whole sentence in one step. A naive solution is to apply CTC loss to train a transformer encoder model. CTC is suitable for the tasks with monotonic alignment between input-output pairs, such as speech recognition. But this condition does not hold in speech translation. In this work, we try to explore the possibilities of using a CTC-based transformer model to perform speech translation. We have two contributions here. First, to improve the translation quality, we propose to apply speech recognition as an auxiliary task in the middle layer of the transformer model. Second, to look into how CTC models achieve non-monotonic mapping, we design a new metric, Reordering correctness, to measure the agreement between the model predict alignment and the ground truth alignment. Now, let me talk more about the reordering correctness score. Given an audio example, who are you? We know the ground truth translation, and we have the hypothesis translation output from the model. We can use the external aligner to align these two translations with the audio transcription respectively. Now we want to measure the proportion of disagreement between these two different alignments. Given a word pair in the transcription, these two words in the word pair will be aligned to different words in the ground truth translation and the hypothesis translation. If one of the alignment direction is crossed, while the other one is not crossed, as shown in this figure, then we increase the number of disagreement by 1. For another situation, if the alignment directions are the same, which means two of them are all crossed or two of them are not crossed, then there is no disagreement in this situation. We collect all possible disagreement and divide the number of disagreement by the number of all possible word pairs. So we can measure the proportion of disagreement between these two alignments and evaluate the reordering capability of the model. However, there is still a problem. If the hypothesis translation is very short, certainly there will be the small number of disagreement. It doesn't mean that the reordering result is very good. Considering this problem, we add brevity penalty to our formula. So now, this proposed score can better evaluate the reordering correctness of a model output. In the experiment, we found that although monotonic alignment did not exist in speech translation task, CTC-based model still performs not bad, and our proposed multitask model can achieve even better performance than CTC baseline model. And it also obtains a speed up around 30 times compared to the autoregressive models. Okay, now my partner Chih-Chiang Chang is going to introduce more detailed results about the reordering correctness.
We demonstrate the reordering phenomenon by two approaches. First, we use the reordering correctness introduced previously to evaluate the performance of our models. As anticipated, autoregressive models show good performance in reordering correctness. Non-autoregressive models perform similarly, but is inferior. This shows that non-autoregressive models also have the ability to reorder. We observed that multitask learning tends to improve reordering correctness. We hypothesize this is due to the improved stability brought by the speech recognition task. Additionally, we investigate the relation between an example's difficulty versus our model's performance. The reordering difficulty is roughly defined as the inverse reorder correctness for a dummy monotonic alignment. Intuitively, this measures how much the reference alignment differs from a monotonic alignment, hence the reordering difficulty. We observe a negative relation between boot score and reordering difficulty. Obviously, autoregressive models are more robust to higher reordering difficulty. It is interesting to see that when applied at layer 8, multitask learning models came close to autoregressive models. Next, we visualize the reordering process by gradient-based visualization. Specifically, we obtain the saliency matrix by computing the gradient norm of output with respect to latent representation of each input. Each column in the saliency matrix is the relative influence of input tokens on the output token. We then aggregate the relative influence of input in each layer for an output token into the reordering matrix. For instance, the figure shows the reordering matrix for the token U. We observed that multitask learning models focus on the corresponding speech segment at lower layers and aggregate the information to the corresponding output position in higher layers. On the contrary, for pure CTC models, there is no clear focus in lower layers, while in higher layers it keeps focusing on the same position. This is a brief introduction to our work. For more details, please refer to our paper or our code. Thanks for listening.